So here we have 2022 October November paper 22 question number 3. Organic compounds can be distinguished using chemical tests and analytical techniques. Table 3.1 shows 4 pairs of organic compounds. And so here we have a table showing 4 different pairs of organic compounds, right? We have A1, A2, B1, B2, C1, C2, and then D1 and D2. Complete table 3.1 to identify a reagent which can distinguish between the compounds in each pair. Give the positive result of the chemical test and identify which compound shows this result. Use a different reagent for each test. Okay, so we're going to start with A1 and A2. What's a test we can use to distinguish between these two compounds? Okay, tell me the reagent that we can use and then tell me which compound will give the positive test as well as the observation. Now, when we talk about a test to distinguish between the two, right, what we're saying is that the test will give a positive result with one of them and not the other one, right? So in A1, we have an aldehyde, and in A2, we have a ketone. And we should know that aldehydes can undergo oxidation to form carboxylic acid, or they can be oxidized to form a salt of a carboxylic acid, right? So aldehydes can be oxidized by acidified dichromate 6 or by acidified manganate 7. So with acidified dichromate 6, we would see a color change from orange to green. With acidified manganate 7, we would see a color change from purple to colorless, right? And aldehydes also contain the CHO group, right? Aldehydes also contain the CHO group. So we can also use Tollens or Felling's reagent. We can use Tollens or Felling's reagent to distinguish between these two compounds. Tollens reagent gives us a silver mirror, right? So we can use Tollens reagent, right? The observation that we get is a silver mirror or a silver precipitate with compound A1, okay, with compound A1. Whereas we get no observation with A2. And if we were to use Felling's reagent, we would get a brick red precipitate. We would get a brick red precipitate with A1, and we would get no observation with A2, right? No color change with A2. So with Felling's reagent is a blue solution that gives us a brick red precipitate if a CHO group is present. Okay, so we can use any one of those 4 reagents. Okay, we can use acidified dichromate 6, acidified manganate 7. The aldehyde will get oxidized to a carboxylic acid. You'll see a color change, right? Or you can use Tollens or Felling's reagent. Those are tests for the CHO groups. Okay, and the aldehyde will get oxidized to the salt of the carboxylic acid. And the observation with Tollens will be that we'll see a silver mirror or a silver precipitate. Okay, how do we distinguish between B1 and B2? B1 and B2 are 2 different ketones. We have pentan 2 on and pentan 3 on. If you notice here, B1 is a methyl ketone. In a methyl ketone, we have a CH3CO group, right? It's a ketone in which the C double bond or the carbonyl carbon is directly bonded to a methyl group. And we can use the iodoform reaction. We've learned that a specific test for this group, the CH3CO group in carbonyl compounds, is alkaline aqueous iodine. That is the iodoform reaction. Right? We can use alkaline aqueous iodine. That's the iodoform reaction. The iodoform reaction is a test for the CH3CO group in carbonyl compounds. B2 doesn't have that CH3CO group. So over here we can use alkaline. We can use alkaline aqueous iodine. Okay, alkaline aqueous iodine. That's just I2 aqueous plus OH minus aqueous. Right, this is the iodoform reaction, and the observation will be that we'll see a pale yellow precipitate. Okay, we'll see a pale yellow precipitate of CHI3. Okay, that's triiodomethane. So we'll observe the formation of a pale yellow precipitate of triiodomethane with compound B1. Okay, with compound B1, that is pentan 2 on, right? What happens here is that the CH3 breaks off. The CH3 breaks off, right? And the CH3 ends up making triiodomethane, right? And then this carbon over here becomes a salt of the carboxylic acid, right? Because it's in alkaline conditions. So we actually get a 5-carbon compound breaking down into a 1-carbon and a 4-carbon compound. We get a 4-carbon salt of the acid here. So we get butanoate, and we get triiodomethane. Okay, how do we distinguish between C1 and C2? C1 is a ketone, right? C1 is a ketone that's hexane 3 on 1, 2, 3, 4, 5, 6 carbons. Ketone group on carbon number 3, hexane 3 on, and C2 is an ester. So we can just use the test for ketones, right? C1 can be identified using 2,4-DNPH, 2,4-dinitrophenylhydrazine. And the observation here is that we see an orange precipitate, right? We see an orange precipitate with C1. And then lastly, we have D1 and D2. How can we distinguish between these two? So one test that immediately comes to mind when we see a carbon-carbon double bond is the use of aqueous bromine, right? We can use aqueous bromine to distinguish between these two compounds, right? Because alkenes undergo electrophilic addition when they react with bromine. So the decolorize aqueous bromine. So the observation would be decolorization of aqueous bromine. Okay, decolorization of aqueous bromine, and that would be observed with compound D2. When we say decolorization, right, the color changes from like an orange brown, right, from a brown solution to a colorless solution. All right, for aqueous bromine, you can write down orange as the color or brown. Okay, orange or brown is the color of the solution. Depending on the concentration, if it's more concentrated, then it's going to be slightly darker brown. If it's lighter, if it's a lower concentration, it's more dilute, then it'll appear more brownish orange. Okay, so decolorization is orange or brown to colorless. Okay, the carbon-carbon double bond will decolorize aqueous bromine. Okay, another test we can use here is actually we have a tertiary alcohol here and a primary alcohol here, right? So the tertiary alcohol cannot be oxidized, whereas primary alcohols undergo oxidation. So we can use acidified dichromate 6 or acidified manganate 7. With acidified dichromate 6, D2 will get oxidized, so we'll see a color change from orange to green. D1 will not get oxidized, the tertiary alcohol. The carbon with the OH is bonded to 3 carbons. Primary alcohol, carbon with the OH is bonded to just 1 carbon and 2 hydrogens. Undergoes oxidation. With manganate 7, the observation with D2 will be purple to colorless. Again, we'll see no observation for D1 or no color change for D1. A1 and A2 are structural isomers. Define structural isomers. Structural isomers are compounds with the same molecular formula but different structural formulae. Okay. Compounds with the same molecular formula but different structural formulae. Give the systematic name of compound B2. Okay, so what is compound B2 over here? Compound B2 is pentan 3 on, right? We have a 5 carbon chain 1, 2, 3, 4, 5. That's pent. All carbon carbon single bonds, so AN pentan, and then the C double bond is on carbon number 3, right? Look at it from either side, you'll see that it's carbon number 3. So compound B2 is pentan 3 on. Okay. B2 is pentan 3 on. Give the molecular formula of compound D1. Okay, compound D1. So over here we have 5 carbon atoms, 1, 2, 3, 4, 5 carbon atoms. There's 10 hydrogens, right? 2, 2, 2, that's 6. There's no hydrogens here. This carbon is showing 4 bonds. Again, the skeletal formula, the CH bonds aren't shown. So each of these carbons is shown making 2 bonds. So you have 2 hydrogens each. That's 6. And then 7, 8, 9, 10. So 5 carbon, C5H10, and then 1 oxygen. So C5H10O. Okay, that's the molecular formula of D1. Okay, C5H10O. D2 forms polymer Z when heated gently. Identify the type of polymer that forms from D2. Okay, so let's look at compound D2. This is compound D2 over here, right? This compound can undergo polymerization. Okay, this compound can undergo polymerization. So it's an alkene. Okay, alkenes undergo addition polymerization. The type of polymer is what we call an addition polymer. Okay, addition polymer. Now, if you have to draw the repeat unit, for this polymer, First, you're going to take the carbon-carbon double bond, okay, because that's the guy that's polymerizing. That's the guy that's polymerizing. And you're going to arrange all the groups on the carbon-carbon double bond above and below that carbon-carbon double bond. So this carbon atom on the double bond is bonded to 2 hydrogens. And then the other carbon atom is bonded to 1 hydrogen, and then it's bonded to a CH2, CH2OH, right? The carbon atom is bonded to a CH2, CH2OH, CH2, CH2OH. So this is the monomer, right? This is the monomer. That's the alkene that we're starting with, right? And then the polymer or the repeat unit over here will be carbon-carbon, right? The pi bond will break. The pi bond will break, and we're going to show the continuation bonds. This carbon is bonded to 2 hydrogens, and then the other carbon is bonded to a hydrogen and a CH2, CH2OH. So this is the structure of the repeat unit. Organic compound E contains 3 carbon atoms. E reacts with cold dilute acidified potassium manganate 7 to form a single compound F with MR is equal to 154.9. Figure 3.1 shows the infrared spectrum of E. Figure 3.2 shows the infrared spectrum of F. So here's the infrared spectrum of E, right? And then figure 3.2, this is the infrared spectrum of F. So both spectra show absorptions between 2850 and 2950 wave numbers, owing to CH bonds in each molecule. Use the 2 infrared spectra in table 3.2 to identify the functional group present only in E. Explain your answer referring only to absorptions at frequencies greater than 1500 wave numbers. So what absorption is present in compound E that wouldn't be present in compound F? Okay. Compound E reacts with cold dilute acidified potassium manganate 7. So what do you think compound E is? What functional group does compound E have? What reacts with cold dilute KMNO4? So alkenes can be oxidized by cold dilute acidified KMNO4 to form diols, right? This is the weak oxidation of alkenes. So alkenes can get oxidized to form diols, right? So this is what weak oxidation does, right? Weak oxidation of alkenes results in the formation of diols. This is an electrophilic addition mechanism, right? This is the only functional group that we've learned that can react with cold dilute acidified KMNO4. So compound E has a carbon-carbon double bond. Whereas compound F doesn't. And the carbon-carbon double bond absorbs infrared radiation in the range 1500 to 1680 wave numbers. And we can clearly see that over here, right? We see that absorption over here around 1600, right? This is due to the carbon-carbon double bond. And we don't see that absorption in the infrared spectrum of F. We don't see that peak in the infrared spectrum of F. Okay, so in compound E, the functional group that's present is an alkene, right? A carbon-carbon double bond. The absorption for that bond is in the range 1500 to 1680 wave numbers. The absorption in the range, right? In the range 1500 to 1680 wave numbers. Use the infrared spectrum of F to identify the functional group formed when E reacts with cold dilute acidified KMNO4. Explain your answer referring only to absorptions at frequencies greater than 1500 wave numbers. So we've already identified that E has a carbon-carbon double bond. It's an alkene that undergoes weak oxidation to form a diol. So compound F is a diol, so it has an OH bond due to a hydroxy group, right? It's an alcohol, it's a diol. So it'll have an absorption in the range 3200 to 3650 wave numbers, right? The OH bond from the alcohol. So we can clearly see that in the infrared spectrum of compound F, right? Compound F has an OH group from an alcohol, and that OH bond absorbs in the range 3200 to 3650 wave numbers. Okay. So what we have over here is the functional group is a hydroxy group. Again, we're just going to take the name from the table given to us, right? In the table it says hydroxy. This refers to an OH from an alcohol, right? Hydroxyl or hydroxy, right? This is an OH bond, and the absorption is in the range. Absorption is in the range 3200 to 3650 wave numbers. The mass spectrum of E shows a molecular ion peak and an M+2 peak of approximately equal abundance at a mass to charge ratio of 120 and 122. Deduce the relative molecular mass of E. Now, whenever we see an M and an M+2 peak, okay, whenever we see an M peak, that's the molecular ion peak, okay, it's referred to as the M or the M plus peak, right? When we see an M peak and an M+2 peak in the mass spectrum of a compound, we know that a halogen is present. This is used to identify the presence of a chlorine or a bromine atom in a compound. Now, in this case, since the M and M+2 peak are roughly of equal abundance, in other words, they're of equal heights, it suggests that there is a bromine atom in this compound. Okay, there's a bromine atom in this compound, right? The M peak is due to a bromine 79, okay, and the M+2 peak is due to a bromine 81. Okay, the M+2 peak is due to a bromine 81. Okay, and bromine 79 and 81 have roughly equal abundances. Okay, the abundance of each of these isotopes is roughly 50%, and therefore their heights are similar. So the molecular ion peak, the M peak, is because of this molecular ion, and the M+2 peak is because of this molecular ion. Okay, we have some R group bonded to a bromine. So now we need to figure out the MR of this compound. Okay, the MR of this compound, we're going to take the relative atomic mass of bromine, okay, to calculate the MR, not the isotopic mass. We're going to take the relative atomic mass. Now the R group over here, the R group has a mass of 120 minus 79, right? The R group has a mass of 120 minus 79. The M peak is at 120. There's a bromine 79 in the M peak, right? And there's an R group. So R plus BR is 120. The BR is 79, so the R is equal to 41. So the R group has a mass of 41. Similarly, we can say that the R group has a mass of 122 minus 81. We can take the M+2 as well. Again, we can figure out that the R group has a mass of 41. So we have a 41 from the R group. Right? And then we would have to take the relative atomic mass of bromine, which is 79.9. Okay, and we get an MR of 120.9. Okay, so 120.9 is the MR. In the R group, we can assume that we have only carbon 12s and hydrogens, because the relative atomic mass of carbon given in the periodic table is just 12.0, right? It's just 12.0. So since the relative atomic mass given is 12.0, right, that's the same as just carbon 12 for our calculations. And the relative atomic mass of hydrogen given is 1.0. And again, so we can just take hydrogen 1 over here. So we don't need to worry about the isotopes of carbon and hydrogen here. Okay, we can take the same mass for the R group as we had in the molecular ion peak. The MR is the weighted average mass or the weighted mean mass of a molecule relative to 1/12 the mass of an atom of carbon 12. Okay, since it's a weighted average mass, we have to use the relative atomic mass of bromine. Okay, so we can't use the relative isotopic masses. The relative atomic mass of bromine from the periodic table is 79.9. Okay, which gives us an MR of 120.9. Use the information in 3 part C to suggest a structure for E. So again, in compound E, there are 3 carbon atoms, right? In compound E, there are 3 carbon atoms. That information is given to us, right? Organic compound E contains 3 carbon atoms, and we figured out that it has a bromine, right? So compound E has a bromine atom and it has 3 carbon atoms, right? Compound E has a bromine atom and it has 3 carbon atoms, right? And it also has a carbon-carbon double bond. So we have carbon-carbon double bond. We have a carbon-carbon double bond. We have 3 carbon atoms and we have a bromine atom over here. Okay, so this is the structure for compound E. Right, if we notice the mass over here is the bromine is 79.9. Right, the bromine is 79.9. The 3 carbon atoms have a mass of 36. Right, and the 5 hydrogens have a mass of 5. and that gives us a mass of 120.9. So this structure is consistent with the information given to us about compound E. Complete the equation for the reaction of E with cold dilute acidified KMnO4 aqueous to form F. In the equation, O represents the oxidizing agent, or oxygen from the oxidizing agent. That's cold dilute acidified manganate 7. So here we have this guy reacting with H2O and O from the oxidizing agent. So we have CH2 double bonded to a CH, CH2Br, right? And this guy is becoming a diol, right? Two OHs are adding on, one on each of these carbons on the double bond. So the product that we get here is, we get a CH2OH, CHOH, CH2Br. If you do have difficulty writing down the structural formula, okay, if you do have difficulty writing down the structural formula, you can just write down the molecular formula, okay? So we have C3H5Br, and since two OH groups are being added, right, we have two extra hydrogens and two extra oxygens. So the product would be C3H7Br O2, okay? So you can use molecular formula for the equation if you have a hard time writing down the structural formula. Although it's always better to write down the structural formula, in some cases they'll require the use of structural formula. In this case, either of these equations is acceptable. C2 can be synthesized using A1 as a single organic reactant. So we can make C2 from A1. Devise a multi-step synthetic route to form C2 from A1. Identify relevant reagents and conditions and state the organic products of each step. Now, A1 is an aldehyde, okay? A1 is an aldehyde, that's propanal. It's a 1, 2, 3 carbon aldehyde, propanal. And C2 is a 6 carbon ester, 1, 2, 3, and then 4, 5, 6, right? So that is propanoate, right? 3 carbon alcohol, and a 3 carbon acid can be reacted to form the ester. Now we have to start with A1. So what we can do is we can take some of A1, okay? We can take a portion of A1. So take a portion of A1, right? That is propanal. The propanal, okay, the propanal over here, that's A1, can be oxidized to form propanoic acid, and it can be reduced to form propan 1-ol. Right? It can be oxidized to form propanoic acid and can be reduced to form propan 1-ol, and then the carboxylic acid and the alcohol can react to form the ester. So in the first step, I can take a part of this sample. I can take some of A1. And reduce it using sodium borohydride aqueous, okay, and heating, and I'll end up getting propan 1-ol. That's CH3, CH2, CH2OH, right? Then I can take a second portion. I can take another portion of A1. Okay, so again, take a fraction of your sample, right, of A1, or take a sample of A1, and I can oxidize it. Okay, and if I oxidize the aldehyde, I can use acidified dichromate 6 or acidified manganate 7. So we'll go with acidified dichromate 6 and heat under reflux. The aldehyde, propanal, will be oxidized to a carboxylic acid. Right? So some of A1 is reduced to propan 1-ol, and some of A1 is oxidized to propanoic acid. Now we have propan 1-ol and propanoic acid. We can react these two to form the ester. Okay, so the primary alcohol can be reacted with the carboxylic acid in the presence of sulfuric acid catalyst, specifically concentrated sulfuric acid. Okay, we can use concentrated sulfuric acid, and we'll end up making the ester. Okay, concentrated sulfuric acid and heat around 60 degrees Celsius, and we end up making the ester. So we get CH3, CH2, CO, right? The CO from the acid bonds to the oxygen from the alcohol. So we get CO and then O, CH2, CH2, CH3. So that's our final product, that is propanoate.